So this is the paper club we do every Friday. And this week, Jessica will present. Jessica, maybe you can say the title of the paper prior to beginning.
Okay, so for this week, we are discussing the paper, The Disagreement Problem in Explainable Machine Learning, a practitioner's perspective.
Awesome. Yeah. So let's kickstart it. Feel free to share your screen on whatever you prefer.
Okay, let me share here. Can you guys see my screen?
Yes. Perfect.
Okay, so one of the reasons I chose this paper is that this author, Hima Lakkaraju, is one of the most influential researchers in explainable AIs nowadays. And this is a very recent work of hers, and she is analyzing how practitioners are leveraging different outputs from explainable AI tools. So basically, the motivations for this is that we still don't have a way to formalize the disagreement between two explanations given by different explainers. And so this is the basis of their work. They conducted interviews with practitioners to understand what this disagreement is. And they created 6 different metrics to quantize the level of disagreement. And they also conducted a study to understand how people are solving these problems. And this is it. The motivation is this. So first of all, why do we need these explainers? In high-stake fields such as we work ourselves, that is finance and healthcare and other fields that need to have stakeholders understanding the decisions of the models, or that may raise ethical questions, we might need models that are explainable, because these models are used to make decisions. So, for instance, a medical model can analyze a picture of a cancer cell and understand which parts of it are cancer. So it is important to be explainable to the humans what the model is outputting. So the explanations that these models give are mostly local for individual predictions. There are also global explainers, but they're not so common. It's more usual that you have local explainers that aggregate the explanations to create a global explanation. We want to understand how faithfully or accurately these explanations are to the model itself. And it's important to note that we are trying to understand what the model is telling us. This might or might not be related itself to the data. There might be some intrinsic characteristics to the data that the model is not capturing, but we can only understand what the model is outputting with these explainers. So the issues that these explainers have is that Sometimes there are studies made with Lime and Shap that those are the most common explainers out there nowadays. These explanations can be inconsistent or unstable and can be prone to fair washing. Fair washing is when you use one of these explanations to try to say, well, my model is fair, or my model is not racially biased, but you're not doing the correct analysis on that, so that is not the conclusion you can make. Also, different models can disagree with each other, and this is what this paper is mostly concerned about, how to understand what to do in case of this disagreement. So here in the related work, they talk about the different types of explainers. There are explainers that are black box or open access to the model. The score can be global or local. As I told you, local is more common. The search technique can be gradient or perturbation. In the case of Lime and Shap, they are perturbation models. So the model will change the set of the features and try to see how that affects the predictions of the model. And there are also gradient-based ones. They are more used to image classification and overall deep learning problems. Also, the basic units of explanation of these models can be different. The feature importance is more common, but there are also rule-based. To analyzing and evaluating these explanations, as I told you, they can be inconsistent, can be prone to fair washing, attacks, can be even unfaithful to the model. They had a study that have shown that some of these tools disagree on this rank correlation. They have one metric that is very similar to this candle-stall correlation that they use to measure the disagreement. They also cite the human factors in explainability. There are some studies that they cite here that say that data scientists are usually not very good at understanding these interpretability tools and techniques. So they are not really able to leverage these results to help them create better machine learning models. So in the next section, they do an interview with 25 data scientists, 30 minutes interviews, to try to understand what these practitioners that can be from the industry or academia, what they consider to be disagreement when they have two explanations from these explanation tools. So these are the most relevant ones that they found. The reasons for disagreement can be because the top features are different. So one of these models says a subset of F features is better, and the other says it's F star, and they are not compatible. The ordering among the top features is different. So especially for the most important features, we would expect that they should be the same, but it's not always the case. So this is also a reason for disagreement. The direction of the top feature contributions is different. So one model can say that a feature like age is related to the model predicting the positive class, And another model explainer can say that this feature is important to predict the negative class. And last is the relative ordering of certain features. So it's about consistency of the order of importance. So if one model says that age is more important than sex, and the other model says the opposite, sex is more important than age as a feature, they also have a disagreement. So in this next chapter, they will formalize the notion of disagreement by showing the metrics that they created to measure the disagreement between two explanations. So the first one are for the top K features. So feature agreement is the most simple of them all. Is basically the fraction of the top K features that are present and in both explanations. The rank agreement is basically the feature agreement plus the rank of these features being the same. The sign agreement is basically the feature agreement and the sign of them, the explanations being the same for a given feature. So if one explanation considers age to be the most important feature, but for the negative class, and the other considers age to be the most important feature, but for the positive class, they have a disagreement, so this is not a match for the sign agreement metric. And the last sign rank agreement is a mix of all these, where you have to have the feature agreement, the rank agreement, and the sign agreement at the same time. Second, they go for features of interest, where the user could give a set of any features they want and calculate the disagreement of the explanations based on that. So the first one is the rank correlation. So here you can use a correlation based on ranks such as Spearman or Candle. And it's basically going to analyze the correlation between the rankings of the features of set F for both explanations. And the pairwise rank agreement, that is basically what I already told you, that is, it's important to have consistency on one feature being more important than the other for both explanations. So in this next chapter here, they explain how they evaluated this metrics. They used tabular, text, and image data sets. So for tabular data, they use two data sets, Compass and German credit. Compass is a much leaner data set with just 7 features, and the German credit has a larger number of features. They evaluated on these models, logistic regression, neural networks, random forest, and boosted trees. For the text data, they use this corpus of news articles, and they used an LSTM to evaluate it. And for the image, they use this ImageNet with 1,000 classes, and they used a ResNet retrained to evaluate that. So they used these methods, explanation methods, to do their experimental analysis. Perturbation-based, there is LIME and SHAP, and gradient-based, there are this vanilla gradient, gradient input, integrated gradients, and smooth grad. I think smooth grad is the most well-known of these. So here is I don't know if you guys can see it clearly. This is the first results for the COMPASS dataset. And in the appendix, you can see all the results for all datasets and all models. There are some interesting insights there. But this is for the COMPASS dataset. So we can see here that for the rank correlation, we have a good correlation here for Lime and SHAP. But for the gradient ones, we don't have it. We have here like a cluster and here another cluster. They call this a dichotomy between these gradient-based models, because these two seem to be consistent with each other, and these two consistent with each other, but not with the others. For pairwise rank agreement, we have similar results. And this is feature agreement, and they show in the appendix different numbers of K. As I told you, the COMPASS just has 7 features. So they show for K equals 1 and 2 to 7. Oops, sorry. So this is the second part for the COMPASS dataset. We can see that the rank agreement is a bit lower here for the Lime and SHAP, and here it's higher again, but it's not the best. So they don't agree that much on the order of the importance of the features. And for the gradients, we have a similar pattern as before. The signed rank agreement is also interesting because it says how the models are interpreting the results. So is the feature important because it affects the positive or the negative class? And it's a lot lower for the signed rank agreement and for the rank agreement, which means that they are considering for some features that they are important for the negative class for one of them and for the positive class for the other. So for the text data, they use this corpus, and they try using 11 words. The words are features here, and they use 11 words at the most. That is the typical length of a sentence. And we can see that the rank correlation is usually not very high. And here is very specific case because Lime and SHAP have the lowest values here for each other, and Lime is more correlated to the gradient-based methods than to SHAP. So they present more distinct evaluations here. And it's overall very low, the rank and sign agreements for text data. For image data, Lime and kernel SHAP can use what they call superpixels as features, while the gradient-based models can only consider the single pixels. And they didn't even put the results here because it was really bad. Like you basically have no correlation here besides this two gradient here. So finally, how are the practitioners solving these problems? They did this qualitative study with interviews with data scientist participants, and they say 13 are from academia and 12 from the industry, so it's almost 50-50. And in the appendix, they show all the questions that they made to these people. So basically, they present something like this. This is an explanation of the feature importance from Lime and from kernel shap. And we can say here that for some features, the sign is different. So for kernel shap, the age is not that important, but it is more related to the negative prediction. And for Lime, it is the most important and related to the positive class. And there's these differences, and here very distinction here is that the race is the most important feature for kernel shap. So this is complicated when you talk about ethical AI and racially biased models, because race being your most important feature when you're trying to evaluate the probability of a person committing a crime again is very controversial. So this is a very tough part to analyze. So basically here, the outline of the study, 25 participants, they use this compass data set that has these features here. And there are several questions about how these practitioners will solve these disagreements. And they are trying to see if there is a method or a pattern that these people use to solve these disagreements, and to try to see if there is something important in what is the one that they choose, or what is their thought process when this disagreement occurs. So here they ask if they think that the explanations agree or disagree with each other, to see if they can define what it is a disagreement. And the respondents were leaning more towards the explanations disagreeing with each other. We're talking about this explanation here. Also, are certain explanations favored over others? And they say there's a high variability in how the participants answer this question and how they solve disagreement. So there is a lack of consensus on how the practitioners are solving this. What is the thought process for people to solve these disagreements? They think about the paper theory that suggests the one model is inherently better than the other, which is very difficult to say. One explanation matches their intuition better, so it's very complicated what is intuition and what is bias for us as humans and data scientist practitioners. And for tabular data, they prefer Lime and shap because they believe that they work best for tabular data. So this is basically it. There are here some sample quotes for each of these types of questions. And well, so what are the conclusions of this? We don't know very much what we're doing. We don't have a consensus. We don't have a very technical way to think about this. We go a lot with our gut to solve the disagreements on this. And this can be a problem, especially for these high stake fields that we're all working on. So this is a very new field of study. People are just now trying to understand better these several explainable tools that were created in the past 3-4 years. And they were created, they were all the rage, and now the researchers are starting to think, well, hold on, do they really help us, and how can we extract more from that? So yeah, the conclusion is that it's not very clear what we are doing, and they say that it's interesting to kind of rethink this problem from scratch and try to develop new algorithms that are built differently, setting a guiding principles to avoid this kind of disagreements. So yeah, I think this is it. I brought this paper mostly for us to have a conversation about this. I found that really interesting. That the conclusion is actually that we don't know what we're doing, and we don't have a clear way to really evaluate that, because for most cases we don't know, we don't have the ground truth for which feature is more important. This is what we are trying to find with these explanations. So this is a very, very tricky part of doing machine learning, and I wanted to bring this discussion here this week.